Great. Now, the topic with which we concluded yesterday's discourse and will resume with in today's class is the frequency domain description of these pulses we are starting to like so much. Okay, the frequency domain description of the pulse, and this is also a sort of review, I suppose, of the pulse whose complete description, again the real valued electric field function as a function of time is script E of t is a half multiplied by the real amplitude and then the complete phase factor in the complex exponent omega naught of t, the carrier part, and the slower variation phi of t. Okay, take a half of that and complex conjugate, you get the real pulse in itself, right. So, now if one takes the frequency domain description of this pulse, then what we do here is the following. We essentially had an intermediate in this case, which is we had E of t to be E of t e to the minus I omega naught t. This is complex. So, we have C c, right. Now, we also had E of t to be square root of I of t exponent, sorry, there should be no minus sign over here, exponent I phi of t. This is the complex amplitude and this is the real amplitude. This is the phase, I will actually call this the or we actually called it the temporal phase ourselves, right. So, we further defined the spectrum of the pulse to essentially be the absolute value square of the Fourier transform of this complex amplitude or this absolute value square of the Fourier transform of the complex amplitude and not yet for the full pulse. What is the difference between the complex amplitude and the total description of the pulse? It is just this phase factor e to the I omega naught t. Omega naught is fixed, please keep that in mind. Throughout any description, omega naught is the carrier frequency this is fixed, and this is a notion we want to hold on to, like holding on to a rock hanging from a cliff in this course, and never let it go, because this will take us through a whole lot of scenarios, although sometimes we may even be challenged about it. This holds for almost all scenarios except some really exotic ones, like what if my pulse consisted only of one optical cycle, then what do I mean by the carrier, what do I mean by the envelope? Until such scenarios which really challenge the definition of a carrier frequency, we really must or rather we are going to use this description to be our bedrock for our understanding. Okay. So, so that is the case. So, now in the complex amplitude, it is simply everything except the fast oscillations of the carrier frequency. So, carrier is fast, carrier frequency is the fastest oscillation that you need to you can have in the pulse or you need to worry about. Everything else is slow compared to it. That is what it literally means. Phi of t is slower than that, I of t is slower than that, and so on and so forth. Whereas, in the case of the single cycle pulse which I have sketched, of course, here horizontal axis is time, this is electric field, this definition is being tested. Yeah, this we need to be careful about it, except there we are doing fine. Okay. So, in such a case, if I now ask for the Fourier transform of this total function, right, which is e tilde of omega, right. Then what do we have here? So, we now use the notion of shifting or taking the Fourier transform of all except e to the power I omega t, right, which is what we call the spectrum, I mean the Fourier transform of the complex amplitude has something to do with the spectrum function, which is S, but then multiplying this with just the mere phase factor e to the I omega naught t does not do anything much to the shape of this, of the amplitude of the spectral amplitude of the Fourier transformed E tilde. It simply causes, in this case, a shift by minus omega naught. Okay. So, this is from the shifting property of the Fourier transform, and then so also a shift here by omega naught in the spectral frequency, which appears in both these terms. So, we have two components, one in the Fourier transform, in Fourier transforming the complete description of the electric field of the pulse, we have one a piece on the positive side of the spectrum, we have one on the negative side of the spectrum. This is absolutely negative, minus omega naught, both omega and omega naught are positive numbers. This is omega naught minus omega, right, typically, yeah. So, this is the omega axis, omega is now a free running variable. So, this is just a shift of the axis to the right, the shift of the axis to the left and the function to the right, essentially by omega naught. Okay. So, in the complex frequency domain of the pulse, now we can essentially we neglect the negative frequency component, because that contains the same information as the positive frequency component, and positive frequencies are what you measure, right. And also we can do away with the center of the, we can also center the pulse on its actual frequency and need not necessarily center it at 0. Okay. In the earlier case, we essentially took this and took away omega naught from it. So, if because omega naught was the carrier frequency, it was central to the pulse, this act of shifting the axis essentially moved this the center to 0, and we do not need to do that. We can keep this at the carrier frequency, and the most commonly used, therefore, complex frequency domain description of the pulse field is E tilde is simply the square root of the spectral amplitude, okay, that the spectral amplitude square root of S of omega. The S of omega is the spectrum of the pulse, or the power spectrum of the pulse, and we have the phase factor e to the I phi of omega. So, now this looks like the absolute value of a complex number multiplied by the phase, okay, a standard complex number form, which we are really comfortable with. Okay. So, therefore, even compare this now to the time domain description of the pulse which we had, where we had and comparing apples to apples, we had E of t written as, oh okay, I should not consider this amplitude. We had the other case. Let us compare this apples to apples by considering E of t square root of I of t e to the, okay, in that case also we had a minus phi of t. Compare these two, except for the symbols t and omega, they look identical, they are the same. So, just as we had an intensity in the time domain, we had a corresponding intensity in the spectral domain, spectral intensity. We had a phase in the time domain, temporal phase, we have a phase function in the spectral domain. So, spectral phase. So, spectrum or spectral intensity and phi spectral phase analogous in the time domain. So, they are just conjugates, it is almost like being just a matter of perception, but that is what it actually is, right, because they are both Fourier related. So, we took note of this and said that look, hey look, so the We can therefore plot the spectrum in using any of these definitions, and a complete description of the pulse is contained in S of omega and phi of omega together. So, it does not matter which description you take, all that matters are the following: the shape of S of omega, the functional form of S of omega is important, the functional form of phi of omega is important. As long as we keep things consistent and know what we are doing, whether we plot this as E tilde of scripted E of omega and the spectral phase, where we also take care of the negative frequencies simply because we can, or we take the other description, this E of omega where the pulse is centered at 0 frequency, it's a relative frequency shift. So, everything else, all other frequencies of interest are essentially a detuning from the, are measured in terms of a detuning from the central frequency, right. We would be really doing fine, right. The shape and form rather of these functions is what's of importance to us. So, we sort of covered this in our earlier discussion. So, in reality, what we want to do is just use only the positive frequency component centered at the actual central frequency or carrier frequency of the pulse, because keeping track of it is enough and B very convenient, it contains all the information. The second thing we want to do is appreciate plotting with two vertical axes, something which we are may not be used to earlier. We usually have one vertical axis. So, here typically in these kind of intensity phase plots, we have the intensity plotted on one vertical axis to the left, the other plotted on one vertical axis, the phase axis to the right. Okay. So, now the spectrum and the spectral phase are as follows. The spectrum of the pulse is essentially, as we saw earlier, the absolute value square of any of the complex descriptions of the pulse described through the absolute value square. So, all these phase factors simply drop off, it does not whether it is the one containing the carrier frequency or not is not important anymore. It is simply dependent only on omega, and this this function is then real valued. For every omega you have a real number. So, and this is very measurable, right. Likewise, if we now took the spectral phase function, this would simply be minus the tan inverse or arctan of the imaginary by the real parts of E tilde, exactly the way we described the temporal phase function, you see. But it could be that one of them is more measurable. This is exactly the point I was making in the earlier lecture. Do we know how to measure it? Our ability to measure ability. Why? Because why are we questioning ourselves? Why the self-doubt? Because of one number which we should keep in mind. Can we deal with 10 to the 14 hertz or one word, one term, petahertz? Do we have the capability of dealing with petahertz frequencies? Probably in modern communication, I mean, okay, on a slightly lighter side, in the context of 6G communications, there is a concept of petabits per second data communication, but that is an entirely different thing altogether. Okay, that could become reality sooner than we think. Yet to measure petahertz frequencies in the true sense of the term, which is like measuring through an oscilloscope, we are not exactly there, although albeit in this course we will kind of we will show realizations of the first petahertz oscilloscope like petahertz oscilloscopy of some form, right, in our course, right. So, therefore, we go to the domain where things are basically reduced, which is reduced in terms of the number of amount of information we need to measure and store, which is the frequency domain, where the information gets compressed into a narrow band of frequencies for regular pulses. So, this is the reason why we are going to like really hang on to the spectral domain, although we always like to talk about the time domain. Okay, measurability and our ability to measure is the key to it. So, now some more new stuff, if you wish, right. So, let us get used to making a sketch of a pulse. So, earlier a somewhat naive sketch of a pulse would be this, right. For a physicist or an electrical engineer, it would sort of be this, and if you are medical, then you have this, well, like an ECG. It's also a description of pulses, right. Yeah, so the point being, we have a notion of a pulse in our mind, which is rudimentary, but not far from the truth. But now we seek a more complete, mature way of having a description of an electromagnetic pulse, an optical pulse, a femtosecond pulse in our mind. In which case, this is what it should look like in a practitioner's mind. That is, a complete pulse description, okay, can either be done in the time domain or the frequency domain. Both are equivalent. So, we invested a lot of time, right, so far in trying to establish the fact that the time domain and the frequency domain are conjugate sort of but equivalent descriptions. In both domains, our picture of the pulse should contain an axis for time or frequency correspondingly, and then we need two axes to describe this in terms of measurable quantities. One, an intensity, we should have called this temporal intensity, but as I said, we think the spectral is the more special one or the odd one. That is just a prejudice, although that is what we will more easily measure. The vertical axis is intensity, the temporal intensity, it is a real valued function, it is a real function, it can be measured. That is also the intensity envelope which we were talking about, and on the other axis we should on both cases have a phase, again the temporal phase and the spectral phase, all right. So, we should have both these this pair of intensity and phase, temporal intensity, temporal phase, or the pair spectral intensity and spectral phase. A knowledge of these two over a sufficiently wide, you can say, range for time and a sufficiently wide range for frequency gives us a complete description of a laser pulse, a light pulse, or for that matter electromagnetic pulse, right. So, here we have chosen to give an example through a Gaussian Fourier transforms into another Gaussian in the frequency domain. The mathematical forms or shapes are the same. Now, here we have used a flat DC function for the temporal phase, that is, the temporal phase remains constant for all time. In this description, in this example, okay. So, the intensity and phase of a Gaussian, in this case with just being a Gaussian, it is real, okay, the entire thing is real. The complex, in the complex description, the way the function phi of t is therefore is set to constant 0. If we have this, then the Fourier transform also reflects a spectral phase which is constant, it is 0, and you get the rest of the description of the pulse in terms of a Gaussian envelope and That's what it is. This is a good example of, from here on, how to think about pulses in terms of their complete description, either in the time domain or the frequency domain. Time axis, frequency axis, intensity, phase, that is temporal intensity, temporal phase, spectral intensity, spectral phase. Okay. So, that is really what is important, and please, another factor that we must note is the following: we should essentially have a sufficiently wide range of coverage in terms of the frequency or time axes, right. Of course, this may not seem as something of importance in a very theoretical or lecture hall description, but if you are going to measure, then you remember that any device that does a frequency measurement over whatever has a limited range. So, we must, as practitioners, question, does my spectrometer have sufficient range to cover enough horizontal axis? Often that is most emphasized, but also sufficient range in the vertical axis. So, you can call the horizontal axis the bandwidth of my spectrometer, and also sufficient dynamic range to measure these spectral amplitudes or spectral intensities. How much dynamic range do I have? That will also determine in real life how well I can measure out my pulse, right. So, the vertical range could be in digital implementations, it could be an 8-bit, or it could be any other 10-bit or 12-bit or 16-bit. That will determine the dynamic range, right. At some level, it is some kind of analog to digital converting device and so on. Those aspects do not change. So, this is very very important too. In the case of real life femtosecond pulses, this is going to get questioned again and again, especially when we measure things in the frequency domain and then talk about the time domain, or we sometimes would do a combined time and frequency domain measurement, as we will see later on. Just to give you an example, it may be a little far fetched, but then think about this whenever you wish. So, we are very fond of describing laser pulses as Gaussians, okay, ultra short pulses. Let us say this width FWHM is 100 femtoseconds. So, what is this the width of? This is full FWHM. If I extrapolate these and consider and set the 0 of my intensity axis to some tail, of this pulse. Is this the true 0 of the vertical scale? Absolute nothing for the signal. We know that the Gaussian tail in principle extends infinitely or whatever, right. This is a notion we have, but in real life, not if this is the time axis, unless we measure, we do not know that the pulse is not like this in reality, where you break the scale and introduce a scale of picoseconds here, whereas here it is femtoseconds. We have done nothing legitimate to measure the so called pedestal of this pulse, unless we have made special efforts to measure it. And what prevented us from getting a full knowledge of it? It is the vertical resolution, or the dynamic range rather, not just the vertical resolution, the dynamic range of our detection. Because in principle, the entire dynamic range, that is why I sketched this 0 with a question mark. Is this my true 0? Where is my noise flow? Is this my true 0? The true 0 is 0 photons, but then you are going to have these femtosecond pulses have huge intensities, a huge concentration of photons at their maximum. So, no detector is going to go all the way from 0 counting a single photon out to this and remain linear all throughout. You see, a single photon detector saturates at 1 photon unless it is a photon number resolving detector, which can also number resolve maybe up to 5 as we speak today in terms of today's technology. If you wish, you can look at the QCMOS detector from Hamamatsu, the company Hamamatsu. Maybe there are others, and I am not promoting any company by saying it. It's just what I happen to know. It's the forefront of technology. While you have other detectors which can deal with higher energy and power densities, but then they will not go down to the single photon range, and you seldom think of this in terms of a single photon detection or no photon. You rather want to see how far you can extend this and get a measure of the pedestal. Okay. So, that is about how much we need to care about the horizontal axis, and it is related to also what we can measure out in terms of the vertical axis, right. So, if you really, I mean, I may be belaboring this point again a little too much, but so be it, since we have begun talking about it. If this pulse on some intensity scale has a value that is something like 10 to the say 18 watts per square centimeter, then even at the pedestal on the picosecond scale, this pedestal could still be something like 10 to the 12 watts per square centimeter. This is already assuming a huge dynamic range of 10 to the 6, which is probably not even real. Maybe we call this 10 to the 16 and 10 to the 11 or 12 or so in the wings. Yeah, I think a contrast of 10 to the 4 is nominal for many lasers. Okay, the reason I am saying this is this intensity 10 to the 16 watts per square centimeter converts to the electric field that the electron experiences in a hydrogen atom. This is a pretty strong field already. So, but now if you are now going to go into the picosecond domain and you have 10 to the 12 watts per square centimeter, this is already the domain of nonlinear optics, right. So, it is not trivial to discuss the pedestal, but in terms of a pulse description, we must be aware of the scales on which we are operating. That is really, really important. Okay. So, now we want to, we not only want pulses, or rather even if we want them, pulses have to be sort of moving in time, right. The clock keeps ticking. If there is one thing that does not stop, it is light. So, then recall the shift theorem. So, if my pulse is propagating in time, all that I mean is the pulse that is here now at a time which is like present was centered elsewhere at some time in the past, right. So, this propagation can happen. Okay. If I now look at the spectrum of the pulse, what happens as a consequence of the pulse getting shifted in time? The following happens, right. The pulse got shifted. Now, remember, this is the picture of the pulse, the Aadhaar card of the pulse, if you wish, right. It has phase, intensity, both are a part of its so called, what I call the Aadhaar card. It is like the Aadhaar number and the portrait, if you wish. Yeah, keep that in mind as a mnemonic for further description. So, basically have this, but then what if it is a nice Gaussian pulse with a flat phase being constant all over in time, in the time in the frequency domain, this act of shifting in the time domain, of course, for the case of Gaussian pulse, retains the Gaussian form, which is owing to the special Fourier transform property of Gaussian functions, but then it simply adds some linear spectral phase to this pulse. Why am I saying that? Why am I saying that it adds a linear spectral phase? Because the initial spectral phase before the shifting was phi of omega, okay, and the pulse essentially had a spectral, in the spectral domain description, E tilde of omega, it had this, right? So, phi of omega is this function. Now, in terms of time shifting by an amount a in time, what got added is the math is trivial, but the idea being that I want to just emphasize the following fact, that it is exponent I phi of omega plus minus a multiplying omega. So, we just added a linear frequency dependent spectral phase.